Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.
I realize I made a little faux pas. I gave away my chairman's seat. But there's one next to it. Okay, so today we'll continue on with our second lecture on photography. Thank you for all coming. I know that we have great competition with the Purdue game starting at noon. I'll make sure we get out on time. Last week, for those of you that weren't here, we worked on lenses. We learned about the physical principles behind lenses, how they work, different types of lenses, some of their weaknesses or aberrations. Today we'll learn about the rest of the camera system that's needed for recording images. And then in the third lecture we'll talk about what actually is recorded, that being light, and what an important role that plays. So without further ado, let's start on exposure. This is, I need a laser pointer. So this is what I put up last time, and we talked about focus and lenses in the last class, or in the last lecture. I keep calling it a class. Today we're going to assume that you know how to focus the lens, you know what a lens is, you've got the right one on. But that by no means guarantees that you have a good photograph. So this photograph is in focus, but it's not a good photograph. So what's wrong with this photo, at least to my eyes, is you lose all the contrast in this part of the bell tower. You can see a few of the brickwork over here, but all of it is gone. It's overexposed. It's absolutely in focus, though. So you can blow a picture not by just having it out of focus, by having it overexposed. The converse of that is have it underexposed. All right? And there's a large range of pictures which are in between. Each of these has a different exposure. And so today's subject is what is exposure and how do you get the right one? Which of these do you like? I think this is the last one. All right. So all of them are in-focus renditions of the bell tower. And you may not agree on which one that you like. Some people might like it a little darker. Some people might like it a little lighter. How are you going to get your camera to produce what you want? This is what I call the holy trinity of photography. We covered aperture size last week. We learned that aperture size was related to the depth of field, and that had a lot to do with the creative expression of our photograph. Did we want to see everything in the photograph, or we just want to concentrate on one subject? So this is the only thing that we've covered so far. Today we need to cover shutter speed and the sensitivity of your sensor, all to give you the proper exposure. You can't have an error in any one of the three and get what you want out. And so this gets actually a little complicated. And there are entire books written on this, and it takes a long time to get it right. And I hope by the end of the day, I won't have taught you how to do it, but I will have taught you what you need to do. Okay? So just to review, for those people that weren't here, the aperture size is the hole in the lens that lets the light through. If we have a large hole in the lens, we're going to have a small depth of field. You can just zoom in on someone's face and have only the face in focus, where the ears and whatever's behind is out of focus. If we reduce that hole in the lens, we increase our depth of field dramatically. And that was the example that I used with Rackham, the graduate school, where we could even see the architectural work on the building, although I was focused almost a block ahead of it on the flowers. So you have artistic control of that. This was covered last week. But of course, what we didn't talk about last week is that by changing the aperture size, you're changing the amount of light that gets to your camera. And that doesn't come without a price. You have to compensate for that. Your camera is not as happy when it has a small aperture as when it has a large aperture. It needs a certain amount of light. Remember, we put that lens in there to collect light, to make it brighter. And then we sort of defeat that purpose by going to these small apertures. Well, we have to pay a certain compensation for that. And that is the amount of light that's left in. I did not give you this definition last week. The focal number, how I talk about these sizes, is related to the focal length of the lens. Now remember, the focal length of the lens was, if I had a small, short focal length, a strong lens, I had a very wide view. And if I had a long lens, those big, long telephoto lenses, I had a very narrow view. So your focal length can go from very short to very long, and your angle of view can go from very wide to very narrow. The aperture diameter is defined to be the focal length of the lens divided by the f number. So if I had 25 millimeter lens and a focal number of 1, then my aperture diameter would be 25 millimeters. And if I went to a focal number of 2, I'd be at half that, 12.5 millimeters. So it's very simple. The higher my focal number, the smaller my aperture, just linearly. Focal numbers on lenses come in this strange sequence of numbers. You never really see 1 unless you're working in a research situation. A fast lens that you'll pay $1,000 for may go down to 1.4, 2, 2, 8, 4, 5, 6, 8, 11, 16, 22. Why do they come up with that strange sequence of numbers? Okay, a little intimidating. It comes up because the intensity of light, the amount of light you're letting through that hole, is proportional to the area of the aperture. Not its diameter, its area. And the aperture area goes as 1 over then the f number squared. So those unusual numbers turn into a nice sequence of 1, 1/2, 1/4, 1/8, 1/16, 32, 64, 128, 256, 512, all powers of 2. So the linear diameter is a strange sequence of numbers, but the aperture area is just powers of 2. So by changing my aperture 1 click up, I reduce the amount of light that gets in by a factor of 2. That's called changing by 1 stop. When you hear photographers say, I stopped down by 2 stops, it means that they have gone clicked down, so they now have 1/4 the amount of light that they had before. Right? So when I stopped down to take that picture of Rackham, I reduced my amount of light a tremendous amount. I went up to f22. I was down 512 times from my original aperture that I was using. I have to compensate for that. We haven't talked about the shutter speed at all. How do I compensate for that reduced amount of light? I have to leave my shutter open for a longer time. All right? And so I thought I would just show you some shutters. So now I'm going to take your picture with a 1-second exposure. That was open for 1 second. That's what you see in your camera. If you hold your camera up and you click it for 1 second, you'll see the iris open up for 1 second. Here's half a second and 1/10 of a second. Most of you are working actually in probably hundredths of a second, right? But I can't show you that. It wouldn't be very interesting. So shutter speed is the length of time it's open. However, your camera really talks about the speed of it in terms of 1 over that time. So on your knob that you dial for speed, you'll see a 10 and a 30 and a 100. Those are 1 over 10, 1 over 30, 1 over 100. So as you go to a larger number, you're getting a shorter length of time. Okay? They use a lot of 1 overs in this. 1 over the length, 1 over the area squared. So exposure is simply how much light did I collect in the length of time the shutter was open through the aperture size that I had. So the quantity of light that I'm collecting is just the aperture area times the time I was open in the shutter. You don't actually use this number, but I think it's really important for you to realize what's going on is you are catching a certain amount of light and you're recording it. So now I'm going to show you equal exposures. All of these apertures are going to take a picture with equal exposures. You ready? 1/10 of a second will be the largest aperture, and the smaller apertures take longer, a lot longer. This has 10 stops being shown. We start out at 1/10 of a second, and the longest one, which I won't make you wait for, is 51.2 seconds. This is 25 seconds, which should click in pretty soon, I believe. It shows you have tremendous range on your camera from very fast pictures, thousandths of a second, all the way up to seconds. So just making a table of what I talked to you about, if I increase one stop, I close down by one stop. To maintain the same exposure, I have to go one time. Oh, time, sorry, I was going the wrong way. Time has to be longer by a factor of 2. Okay? Conversely, if I want to let more light in, I open up one stop, and then I have to take a shorter duration time it's open. Okay. And you can just equivalently get the same picture, same exposure, at any one of those settings. Now, why would you want to change the shutter time? You already know why you might want to change the aperture. Have a small depth of field, have a large depth of field. But why would you want to change the length of time your shutter is open? Well, there are two large reasons. Motion blur. The first is motion of the camera. If you're shaking the camera, that's not a good way to take a picture that's clear. Your camera can be in focus, but if you're shaking it, you'll still get a blurry picture. The other reason you might want to move the camera is you might want to intentionally pan, and I'll tell you what that is. Of course, you also have the motion of the subject. You may want to freeze the motion of the subject, just stop it, or you may want to blur it for some artistic reason. Okay? So you have to think about all of these and motion blur in setting up what shutter speed you're going to pick. So let me show you a demonstration. You saw this camera. We saw it take a picture of a Christmas tree in the last class, and it was in focus. We had adjusted the lens to get it in focus. But now you're trembling from your morning eggnog, and you see that even though it was in focus, all those rays came to a point here. The fact that you were shaking the camera makes the image be blurry. Okay? We had too long of the shutter time. All right? So we're going to do a little bit of mathematics here. How fast should a shutter be if we want to be able to stop your shaking? Okay? Let's say that the field of view of a lens is theta sub lens. In other words, it's 110 degrees, it's 90 degrees, it's 3 degrees for my very small telephoto lenses. And we studied that in the last class. We showed that the field of view was this red curve. We said that for very short lenses, we had a large field of view. And that for very long lenses, remember the 1200 millimeter lens, I think had a 3 degree or maybe 1.5. I've forgotten exactly what this was out here. But I never gave you this formula, that the angle of the lens is a constant divided by the focal length. This looks like 1 over the variable. Gets big when the variable is small, gets small when the variable is big. This number is a particular feature of my camera. Your camera might be a little different. Okay? But I fit this, and it's the red line. It fits the data really well. So I want my shaking, the change in the angle per time, times the time my shutter is open, to be less than 1/1000th of that field of view. Now why, 1/3000th of that field of view. Now why did I pick that? It so happened that I have 3,000 pixels in my sensor. And so I wanted my shaking not to be more than 1 pixel. It's arbitrary. I could have had 2 pixels if I weren't so critical. But this is what I chose. And so if I combine the field of view of my lens with my criteria for a sharp picture, I get that 1 over my shutter period, the length of time I'm open, should be less than 1 over 3,000, 1,800 times the focal length times 1 over delta theta delta t. Now let me make sure you understand what delta theta delta t is. Those of you who are having flashbacks to your calculus class, this won't be that painful. Delta theta delta t is the rate at which the camera is shaking. How many degrees per second? So if I'm really wiggly, I might be going 45 degrees per second. Hopefully I'm on a ship. But if I'm holding it still, I might be 1 degree per second. Okay? It's just the rate at which I'm shaking. To do that, we needed to to find out what my rate of shaking is, we needed to do an experiment. So we came down yesterday with my camera, and we modified it slightly by putting this very Arnold Schwarzenegger-like laser pointer on it so that I can now target someone's forehead. And I stood back here, and I held the camera up. I guess it'd be good if I take the lens cap off. At the A. Maybe I'll even zoom in so I can see the A. And that's about as well as I do. Did it jump when I took the picture? Could you see it jump? I mean, I can't tell because the mirror that goes blank. Did it jump a bit? A little bit? Okay. That jumping is actually the dominant jitter that you have when you touch the camera. Now, that experiment is right here. Okay, that's me aiming at the A. I had a second camera, which we set right over here, and we took a 1-second exposure. So we had the shutter open for 1 second, keeping a trace of me shaking around. Okay, so that's what was going on there. And I'm supposed to have tripped the shutter somewhere in between. It's probably this big jag out here, or something like that. We did a second experiment where the camera was held differently. The camera was held out here, like so many people hold their Instamatic digitals. And they are shaking all over the place because they're looking not at their target, they're looking on their screen where they can't see a thing. And you get a much bigger. All right? God gave you a nose. You might think it's for smelling. It's not. It's for anchoring your camera. Put the camera up to your face and hold it there. Those of us with bigger noses are steadier. All right, so, but out of this, I was able to make an estimate of my shaking rate. And let me turn this off for a second. So what I said was, crudely, and now you're going to get to see real physics in action. I said, oh, I went up and down this about 3 times. This is an 8-inch brick. Therefore, I moved about 1 foot. That's just the way physicists think. I moved about 1 foot, and I was 60 feet away. We were standing right over there by Warren. And so the angle that this was moving was about 1 foot divided by 60 feet. That's the angle in radians. You don't have to worry about it. Just take my word for it. I then multiplied times 360 over 2 pi to convert to degrees. I divide by 1 second because I moved that 1 foot in a second, and I get a miracle. 0.95 seconds per degree. Close enough to 1 for me, 1 degree per second. That's what we shake, roughly. This person's a bit more, this person's a little bit less. Let me put that into our formula now. This is just going back. We've now experimentally determined this quantity. And the fastest algebra you'll see, we get 1 over our length of shutter time will be 0.6 times the focal length. Physicists can never remember decimals, and so this becomes 1 over the focal length. And this is a famous rule that to stop your camera from shaking, 1 over the period of time the shutter is open has to be less than 1 over the focal length, the 1 over f rule, which some of you may have heard, but I'm sure you've never seen it actually derived. So the 1 over focal length rule says that if I'm using a 100 millimeter lens, something that has a field of view like this, I had better be shooting with a time that is less than 1 over 100th of a second. So that knob on your camera had better be at 100, 200, 300, 400, or else it'll be blurred by motion. Conversely, as I go to longer lenses and smaller angles, I have to get real fast. And you will notice, remember when I told you that picture of the flower that I took with that really long lens, I said it's blurry. I didn't make this. That's why it was blurry. All right? When you get up to those speeds, wind, pulse, everything plays a role. Now, there's a key part of this rule right there. If handheld. You can beat this rule, you can forget this rule if you do what the pros do. The major difference between a pro and an amateur is the use of a tripod. It is the #1 reason the pros get better pictures than you do. I think I'll put it out here. So let's repeat that experiment with the camera on a tripod. Make sure I don't pinpoint anyone for a termination over there. All right. That's not jittering, or it's not jittering much. Now I'll take a picture. You didn't see it. If I want to take a good picture, I actually put a remote control on this and I click the remote control rather than the camera body. That's what the pros do. And they don't just do it sometimes. They do it all the time. If you want to take good pictures, you use a tripod. Number one difference. And it's all because they now have complete freedom of what shutter to use. Before, I don't know how many people I've blinded in the audience with this. I know Warren is thinking, God, he's blinding the audience. Weren't you, Warren? They have complete freedom to pick whatever aperture they want because they have complete freedom to pick whatever shutter speed they want because they're not worried about following the 1/f rule. All right? Okay. So now if all my exposures are equal, I'm putting my stuff up on a tripod. I can use whatever aperture I want. I can use whatever shutter speed I want. Then how do I decide what to do? Well, I've given you some hints about that. What's your depth of field is going to help you pick what aperture you want. But what subject do you have? In this picture, you want the flowers that are blowing in the wind to be frozen, but I wasn't trying to freeze the wing of the hummingbird. That's beating several hundred times a second, and actually to freeze that, I would have had to go on to a much, much faster either speed of film or a much, much faster shutter speed than I wanted. Plus, when I see a hummingbird, I just see a blur for its wings anyway. So this is what looked natural to me. So I want to stop this, but not that. Depends on your subject, what speed. Now, last night, as I was lying in bed going through this talk, my wife leans over when she sees this and says, "Why are you showing a blurry picture of a seagull?" First of all, this is not a seagull. This is a tern, not a flying rat. Second of all, when you are an artist, there is only one person you're trying to satisfy, and that's yourself. Remember that as you get better in photography and you experiment and you want more than just getting things in focus for the family album, you're going to have some pictures that other people don't like, but you will. This is an abstract picture. This is a picture which is about form. This is not a bird book on terns. So it's supposed to have motion, and the preponderance of white is supposed to be artistic. We suffer, we artists. Even us husbands suffer. Okay, here, fireworks. It's no fun to take a firework picture and just stop everything in motion. You want these trails. It's a 2-second exposure. Take fireworks, get that aperture down small. You take them at night, everyone opens up their aperture. It's night, I'm going to use a really big hole. No! Make a small hole and go for a long time. Okay, this is like F11, 2 seconds. It's a rock. But is it a rock in water or a rock floating in the clouds? Okay, it's in water. But it's also a very long exposure, so the water has come in and out. And if you let water come in and out in the surf, you'll turn it into something that looks like cotton. The rock is absolutely clear, glistening with water on a good screen. And this looks very heavenly. It's another artistic picture, which some may like and some may not. And this screen, by the way, does not do justice. Okay, it's becoming autumn. And I went out and saw this beautiful maple tree. And the sun was setting, it was gorgeous, and the wind was howling. I could not freeze the motion of that tree for anything. Everything I got was blurry, so I went with it. Right, this is something like half a second or a second. And it's just color of autumn blowing in the wind. You either like it or you don't. It's either an out-of-focus tree or it's a palette of color. But I got to pick. I got to pick which it was. Here's an interesting combination of using a slow shutter speed with a flash. Sometimes you'll see a lot of Sports Illustrated pictures where the person they're just frozen. And that can be really cool. But you might lose the perception of motion. So if you take a picture which is sort of like a quarter of a second, and then you put your flash at the end of it, you get both. You get the person moving, and then you catch them at the end. And so you get this perception of the person moving, and then a pretty clear picture because you caught them with a flash. That's a more sophisticated technique. I don't know how well I did it here, but I gave it a try, and one that you can play with. Once you've got it down that you can freeze a person, then you can play with it this way. I shoot a lot of plays and drama for the high school and the Burns Park Players, and it's really dark. I mean, you're always at your maximum sensitivity. You're shooting, you're holding it like this, because you really can't use a tripod to follow anyone. You're holding it like this, and he is pretty clear, but the dancer is blurred. And I really like this. I like the motion of him watching this floating through the air. It was by accident. Didn't plan it. You take enough pictures, a few of them, a stop clock is right twice a day. Here's the one, you froze it. Michigan playing Wisconsin volleyball a couple weeks ago. Right at the peak of her jump, she's frozen. No flash, no nothing, just use a fast enough shutter. Sports, you need to use something around 1/500th of a second. This doesn't have very good light, so I had to kick my aperture all the way open. There's not very large depth of field here. And I also had to use something I'm going to talk about in a moment, high sensitivity shutter. Here's one where you stop a person, okay? And maybe you get the perception of motion here. All right. So you now know about aperture, how big the hole is, the shutter time, how long the shutter is open, and so the product of those is the quantity of light. If it were simple, that would just determine whether something is bright or dark, but it's not quite that simple. That amount of light can be rendered as a dark spot, or dim, or medium, or bright, or white, all determined by the sensitivity of your sensor. In other words, if I have this quantity of light, and I give it to some film that's very sensitive, it's going to render it as bright. But if I give it to some film which is not very sensitive, it will render it as dim. And so there's a third thing in this holy trinity, which is the sensor speed or the ISO rating. I'll sort of try to flip back and forth by that. That's what everyone in the field will call it ISO, which I didn't even look up and see what it meant. It's probably historical from film. The quantity of light is the product of these two. Your depth of field is determined by your aperture size, and your motion blur is determined by your shutter speed. This is what you have to master as a photographer, and it isn't easy. It's not easy. It will take months if you really try to do this. We have talked about aperture size and shutter speed. Now I'm going to talk about the sensor, which could either be film or digital, CCD. And I'll spend most of my time talking about digital because most new cameras sold nowadays are digital. There are still people using film, and there's nothing wrong with that. They use film because they believe the image quality, the color rendition of it is better. If you're a pro, and if you believe that the color is better with film, it's your livelihood, you use film, period. They do, however, almost always use slide film and then immediately scan it and digitize it. So most of what I'm going to be saying is actually part of them farther down the line, but they originally take that picture with film. Here are some of the major differences between film and a CCD. You don't have film costs. So you think, it's going to save me money. No, no. You need to buy a computer. And that computer goes out of date in 2 years. So you're spending a couple $1,000s every 2 or 3 years. That's a lot of film. You don't really save. The sensor size on the digital cameras is predominantly smaller than the sensor size used in film, and that makes a difference. It can be both a benefit or a disadvantage, depending on what you're doing, but you have to know it is different. They're starting now to have 35mm digital cameras. They're quite expensive. They're about $5,000 and above, but they're there, and they'll probably come down. Image quality is hotly debated. It's like music. Which one do you like better? Chopin, Beethoven. Mine's better than yours, that sort of stuff. If yours is what you want, great, use whatever you like. The noise characteristics are different between film and CCD. Before I go on to the really go into digital sensors, actually, I want you to remember back to last semester. Professor Kurdak, who gave the introduction today, in his lectures on miniaturization electronics, spent some time on CCDs and went into some of the physics behind the actual operation of that. Since you remember that, I'm sure, I won't go into it now. But I will talk about these in a highly sophisticated way by calling them photo buckets. They are what collect that quantity of light. Now, I've been talking about and trying to get you to realize that there's a quantity of light that you have caught in your camera, and it's gone into this photo bucket. All right? Why don't we turn the lights on and make this more vividly apparent to you? We have here one of our famous lecture demo creations. This is the model of a camera. And in this camera, we have all the functional parts that I've been talking about. We have an aperture, we have a shutter speed, we have a sensor, and we have light. Light is water for this camera. And so water, you want to turn this on, Warren? See, this is the dangerous part. If he turns it on too high, water splashes the front row. I don't want to be responsible for that. Now he's scared. Water will play the role of light. What does light do for a camera? It comes in and it goes through the aperture. These finely crafted, they look like the cleanup pans on your stove. They have different size holes cut out in them for different F numbers. These are going to be your apertures or your iris. We have a photo bucket down here, which is a bucket, all right, where we're going to collect the water. And we have a way of measuring how much light we have in our bucket because we're going to weigh the water. That's how we tell how much light is in there, by weighing it. Okay, so are we ready to take a picture? Let me, so we have to switch this on. Okay, we're on. So the weight here is going to be the bright or the quantity of light that we've caught. Let me zero it so we start out with a fair test. We're zeroed. Are we ready to take a picture? Let's take a 10-second exposure. It's kind of a slow camera. Are we ready? I think it's always dangerous first time. Right now we are collecting light. Our picture's done. We have collected 2.86 units of light in our bucket. All right, let's give Warren a hand. He worked very hard on this. Okay, so let's say that was too much. That's too bright. What can I do? There are two correct answers. I can change the aperture or I can change the length of exposure. So first, let's change the aperture. I'm going to a smaller aperture, an aperture which is 1/2 what the previous one was. I have to get this on or our camera can spill. I set it to the same exposure time. Do I want to cut it down? Yeah, I'll cut it down. And what should our answer be? Half this. Quickly, what's half that? 1.45. All right, 1.45. We'll zero it. See how good we are. 10 seconds, ready? Oh, I have to adjust my aperture just a bit. Not bad, not bad. The aperture was a little off-center. A little smaller than it should have been. But we cut it in half. We just made our photo darker by letting less amount of light in. Okay? Now, you will probably believe me if I were to go for 20 seconds that we would get back to where we originally had. Okay? You'll buy that. But let's do something that happens in real life all the time. Let's go back to our bigger... Oh, let's stay with our small aperture, and let's reduce the brightness of the day. Okay? That means we have to reduce the amount of water that's coming from whatever our source is. So now we're going to ask Warren to turn the valve closed on the faucet so the water runs a little less quickly. Or actually, it can run a lot less quickly if you'd like. And we'll expose this for 10 seconds again. Ready? I have to zero. I did zero it. Okay. Make sure it's zero. Wait, just let it go. Let it go, Warren. Let it go. Let it go. Just let it go. Now, that is a picture that's underexposed. Don't change it. Don't change it. So when you have a picture which is underexposed, but I want that aperture and I want that length of time for artistic reasons, what do? I increase the sensitivity of my detector. I increase my film speed. I increase my ISO. Now, on this scale, we do that in a creative way. This is being measured in ounces. If I want to measure it more sensitively, I change it to grams, which gives me a factor of 30 enhancement, 30 in speed. So let me change the units here. When it's more sensitive, you get more noise. So that's the cost of going to more sensitivity. Do you think this will work, Warren? Okay. Ready? 10 second. We got 10-second exposure. Oh, what was that?
Pressure buildup.
Pressure buildup. All right, then we have to start over. We got to get rid of that pressure buildup. I understand. Let's go. Oh. You know what? Okay, I know how to deal with this. I'll give it a 12-second exposure, and I'll re-zero it after second 2. Are we ready? 1, 2, all right, re-zero. What? Wait, it's going.
Yeah, but we're not slow.
All right, give me some flow. Give me some light. You think you got it? These people in the front row are getting nervous.
Yeah, well, I'll get wet first. Okay.
All right, we're ready. All right, that's better. It got some flow. Okay. And you see the number is much larger. That number in your camera, that's actually what's going on in your camera. Your camera is actually getting a number. It's an analog signal, but a voltage is so high or something. And what they do with this changing of scales is they put an amplifier in it. So when you're at bright scenes, you don't amplify your signal very much, but if you're at dark scenes, you put an amplifier in that enhances it. That's exactly what they're doing here. We don't have someone inside there changing from English to metric units. We just put an amplifier in there by a factor of 30. So in your camera, you often have something like a factor of 10, maybe 20, change in your sensitivity. This camera, we changed by a factor of 30. So in some ways, it was more sensitive than mine. In other ways, since it got all wet, it's not the same as mine. The other thing that you see about this is we don't have just one bucket in our camera. We have 3 buckets. And that's because I don't want to take a picture of just one color, but I want to take a picture of all the different colors. And so it turns out, and I'll discuss this much more extensively in the next class, that by having red, green, and blue, you can make a large number of colors. And by recording the intensity in just the blue light that gets through, just the green light, just the red light that gets through, you can make your color pictures. So they put a filter over this and say, let me only collect the blue water. Let me only collect the red water. And then they look at those ratios and they produce colors. I will talk about that a lot, or extensively flesh that out in the next class, how that's done. This is the pattern. This was a 1-pixel camera. Did not have great resolution. Most modern cameras are on the order of 5 megapixels, 5 million pixels. There are 1,000 by 1,000 would be 1 million pixels. My camera is 2,000 by 3,000, so it's a 6 megapixel camera. They now have 25 megapixel cameras. And we'll talk about some of this before, what all of it's buying you. But it's buying you more buckets. More buckets where you can record red, green, and blue. And you can take the reading from each of those buckets to tell you whether it's dim or bright. Is it heavy or light? All right? They weigh it each time. So every time you take a picture, you let light in. You let the red, green, and blue light get collected in these buckets. You then weigh how much light is there, and you turn that into a color photograph. It's really amazing that it works as well as it does. This is called a Bayer pattern. It was invented by Mr. Bayer at Kodak, and he now has come up with a new scheme which he thinks is better than this, and we may be seeing in cameras in the next couple years. All right, so I thought this was appropriate for today, since all those people are at the stadium looking at the big M. Here is a picture, and if I blow it up a lot, so that I'm just looking at the edge of the M, you can begin to see pixels, just barely. When you have 6 million of them, it is actually hard to be able to see individual pixels. All right, but you see that there's some yellow going over here in this blue, and this little sort of round blots, those are actually pixels. So that is an incredibly small area, of this section of the M. It's probably no bigger than the spot of the laser pointer. Now, we've had to not let our camera make this feel bad. We wanted to take our own picture with the water camera, and so we did. I'll let Warren switch it. You could imagine us taking, how many, what is this, 13 by? 13 by 260, 30 by 160, 13 by 13, 269? 169, thank you very much. 169. We have 169 pixels here, and all we would have to do with that camera is to run it 169 times, each putting in the right amount of blue and yellow water, and we would create this mosaic, which looks a lot like mine. If we flip back, mine. If you use your imagination, some. All right? So it does help to have more pixels in the sense of having finer resolution. But I will tell you, my prejudice right now is that when you go to the store and the salesman says you have umpteen zillion megapixels, most of that is marketing. And so we can talk about that a lot more when we talk about camera specifics.
Where's the camera there?
The camera, Warren had to climb the catwalk and scaffold earlier this morning to mount the camera right up there. Once again, sparing no expense and danger for Saturday morning physics. Let's pull this out a little bit. I don't know if I dare unhook it. Someone may want to have us do it again. We have to get out way of the dynamic range. So the next thing I want to talk about is the dynamic range. Dynamic range is a new concept in photography, at least for you guys, because I haven't mentioned it to you, and it's very important, involves the sensor. Dynamic range is the range over which an instrument can actually measure something. So let's take your speedometer. If you go as fast on your car as you can, maybe your speedometer can go all the way to the far end and just stay there, even though you're going faster. You've exceeded your dynamic range. Your speedometer goes from 0 to 100, and you're going 110, but it still reads 100. You've gone off scale. I don't quite know how to go less than 0, and I think backwards doesn't work quite right, so this doesn't work very well for that. But photographs can go off both ends. They can be too dark or too light. So you can go off the top end or you can go off the bottom end. This wrecks as many pictures as being out of focus or having motion blur. This wrecks equally many, and it's more subtle because people don't know what it is. We'll flip this on, turn our lights down. This was made by a graduate student of mine who was very proud of it. He called me on the phone, left a message. I spent my entire day making one of your lectures for Saturday morning physics. So I delayed his graduation by a day. What we have here is, I think 9 or is it 10? 10 LEDs, each one doubling in brightness. Can you see it? Do we need to have another light turned off? They're bright enough? Okay. So the very dimmest one, you may just be able to see. At least you're supposed to be able to see it. And the bright one, if you actually look at it straight on, it gets painful. I mean, it's not going to hurt your eye, but it's painful there. So we have what's known as 10 stops of illumination. My camera, I came over here and I took a picture of this and looked at what my camera could actually resolve. If I tried to get the pixels all the way down to the darkest one, so you can just see it there, you guys should just be able to see it. These 4 are overexposed. And it's not so clear to you, but I can actually go in there and look at the center of these and see that I've gone off range. Off range for me means 256, because it's an 8-bit scale. I can see that these they're all the same brightness, even though they're doubling in power over here. If I move my camera so I no longer can see these, they're just black, then I can still get overexposed, but now these are all different. The dynamic range of my camera is about 5 or 6 stops. I can record 5 or 6, 2 to the 5 or 6 in power of intensity of light. If something in my picture is brighter, it's going to have the same color no matter how bright it is. If something is dimmer, it's going to be black, no matter how dim it is. And this wrecks a lot of photographs for a lot of people. All right? And it is a problem because digital cameras have this 5 or 6 stops, and if you have a small pocket camera, I think we can flip it up. If you have a small pocket camera, this is closer to 5. If you're coming from print film, you had maybe 7 stops. So you're used to being able to get a factor of 4 larger dynamic range than you can with your digital camera. So pictures that worked for you in film now are either too dark or too light when you were the digital camera. It's not your fault. It's the sensor's fault. This is a place that the digital sensors are lagging behind film. This happens to be about the same dynamic range as slide film, however. So professional photographers have always been working with this limitation, but people who have been shooting prints have not. And it's an adjustment. You have on a digital camera an extremely useful device to let you know whether you're utilizing your dynamic range or not, and that's the histogram. How many people turned off their histogram on their camera because there's this splotch in the middle of their picture and they didn't like it? Come on, some of you did. This contains an enormous amount of information. The histogram, down here, it's telling you about the darker tones in your picture. These are the mid-tones, and these are the highlights in your picture. And it's telling you how many of them you have. I have a lot of mid-tones. In fact, this picture only has mid-tones. There are no darks, and there are no lights. This is a picture that would be boring. It would be more monotone. You haven't extended your dynamic range. This is a picture that's relatively properly exposed. You've used all of your dynamic range. You have some things that are dark. You have some things that are bright. The majority of your picture are in the mid-tones. That'll be a properly exposed picture, and it'll look good. This is what you want to avoid. These lines on the end. Those are things that are outside the dynamic range. Here, we have a bunch of stuff in the image that's rendered too dark. That's going to be black. And you will make no distinction between those blacks. And this is going to be white. And you will make no distinction between those whites. Okay? This is not typically a properly exposed photograph. And that information is given to you in your digital camera, and it's incredibly useful. If you see this, it tells you the amount of light you're getting is too large. Change your shutter speed so it's faster, or reduce your aperture. And then you'll get a better photograph. So you have instant feedback. You don't have to wait to go to the film store, get it processed, get the film back, and say, oh, I made a mistake. That's the beauty of a digital camera right there. So watch your dynamic range. I got to watch my time. So we had an ice storm last year on the Diag. Real easy to blow a picture like this, getting the ice to be too bright, getting the darks to be too dark. This spans the full dynamic range of my camera, from light to dark. Whenever you're looking into the sun, that beautiful sunset and that scenery around should be screaming out to you, difficult picture. You have got lights, you have got darks. And unless you're careful about it, and once again, this camera doesn't do this justice, you're going to blow the picture. This is a picture that automatic exposure will not handle well. How many of you have taken pictures out in the snow and found the snow is gray? Gray because when you have it on automatic exposure, it says whatever's out there is average. And I'm going to make it average. Remember that if you give the camera the intelligence, it's going to take the quantity of light, and it can put it wherever it wants, dark, bright, medium, and it puts it average. And so it turns snow average. Well, snow is not average. Snow is bright. On a good monitor, you can actually see the fur along the buffalo. So I'm able to see the differences in the dark and maintain the granularity in the snow. It's not all white. Snow is not perfect white. It's got texture to it, so you can't blow out your snow either. Can you just see the lines in the feather? It's better on my monitor, take my word for it. And you can just see the lines in this feather from light to dark. All right, you have the whole thing. I happen to have birds here. You can still see the feathers, and this is completely black. I couldn't hold the dynamic range, all right? But I was willing to pay that price because I wanted your eye up here, and I didn't care so much about that. So I made a choice of keeping the lights, getting rid of the darks. I could have made the other choice of blowing the whites and keeping the breast feathers. That's not as interesting a picture. So you get to make your choice. You pay a price by going to higher sensitivity. When we went to grams, which had a factor of 30 amplification, I told you about the noise, the fluctuations in that reading. Here's a picture, a very dark scene from Cyrano de Bergerac, which is over at Huron. If I blow up right, it's so hard to see here. Can you see speckles of color in this? Anything? No, there are. They're little speckles of color. Little white, little dark, white, little dark. And if you were to print it out, you would see that. That's sensor noise. That's little bits of light which is getting into the sense. Professor Kurdak talked about noise in his devices. It's called dark current. If you had no light at all, you would still read some signal. It'd be like water leaking in from the side of the bucket. And if you really have no signal and you've turned your sensor way up, then that noise appears in the dark areas of your photograph. And professionals don't like it. They work hard to keep it away. It might not bother you, but that's the type of noise. Here is just sky done with a professional camera. If we just look at one color, this is really what I want you to look at. The small Instamatic digital cameras have appreciably, do you see the red flicks in there? And here you can see it pretty dramatically, have appreciably more noise than these cameras, which I could talk about. If you move up the sensitivity, right here they've turned up the gain a factor of 8, it gets horrible. Why is that so bad from these professional type cameras to your little Instamatic. It's bad because each photo bucket has gotten smaller. Professor Kurdak spent the entire day telling you how smaller was better. That's not true when you're talking about photo buckets. Having a bigger photo bucket, one, makes it more sensitive because you're collecting over a larger area, and two, makes you less sensitive to fluctuations in it. So when you buy a small camera where they tell you this has got 12 million pixels, they're telling you it has 12 million small pixels that aren't very good. And my camera, which only has 6 million pixels, has 6 million pixels that are 20 or 30 times larger and much less noisy. All right? So beware the high megapixels line. You want to know what you're getting. And when you get 12 megapixels in a space this big, they're small megapixels. They're small pixels. You can set your camera on automatic exposure, and these cameras will do everything for you but buy you lunch. What I'm suggesting in this lecture is you will often get very reasonable pictures. This is automatic exposure. But if you want to have creative control, if you want to be able to worry about your depth of field, motion blur, then you have to go a little deeper with your camera and learn how some of the controls work a little bit more. And most digital cameras will allow you to do that nowadays. So hopefully, today, I have introduced you to this holy trinity of photography and how the playoff between how large an aperture I use, how fast my shutter is, and what sensitivity I'm recording it on will tame or allow you to work with depth of field, motion blur, so that you can create the pictures that you want. So once again, I have to thank Warren, Mark, Emily, and now Chris Kelly for all the demos that are up there. They spend a lot of time. Let's give them a hand. Carol and Candy for all the publicity, arranging the food for you, handing things out, making sure you guys are comfortable. Let's give them a round of applause. I have to mention this is Carol's first day back at Saturday Morning Physics for maybe 6 months or 8 months, and so she's very glad to be back. We're glad to have her back. And next week, it's all about light. Right now, you have been armed with the knowledge of how to take good pictures. Next week, we talk about what it is you actually record, light. And there's a lot to learn about light, both from a scientific and an artistic point of view, to take a good picture. So I hope to see you next week.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.